In the last lecture, we have seen beta functions, and then we have solved some examples based on beta function. Okay, so let us try to solve some more examples. Okay.
Sir,
Yeah.
sir, I have one doubt. In the definition of beta function, we have written let m comma n be greater than 0, then convergent integral. What do we mean by convergent integral?
Yes. Convergent integral means which will give you a finite value.
Okay, sir, got it. Means definite integral, right?
Definite integral means what? Which has the limits given. That we called as definite integral. Okay, the integral with the limits we called it as definite integral. Convergent means with the integral with the finite value. Okay.
Okay, sir.
Yes. This is improper integral. So the convergence for the improper integral is guaranteed when m and n are greater than 0. Okay, then only this integral will be convergent integral. If m is negative or n is negative, then this improper integral is not convergent. That's why we cannot call this function or this integral as a beta function. So only convergent integral, we call it as a beta function. Got it?
Yes, sir, got it.
That's good. Okay, so let us see the property or the duplication formula. So I hope all of you are able to see this journal. Are you able to see the journal?
Yes, sir.
Yes. Okay. Good. Okay, so we need to understand what is duplication formula. Okay, so let us try to prove the duplication formula. So what we have, let beta mn is equal to twice integral 0 to pi by 2 sine raised to 2m minus 1 theta cos raised to 2n minus 1 theta and d theta. This is what we know about the trigonometric definition of beta, right? So here, what I'll do is, I'll put m equal to n. So if we put m is equal to n, what we are able to get? So we get beta of mm. This is equal to twice integral 0 to pi by 2 sine raised to 2m minus 1 theta cos raised to 2m minus 1 theta and d theta. So this is equal to twice 0 to pi by 2. Can we write it like this? Sine theta into cos theta bracket raised to 2m minus 1 d theta.
Yes, sir.
Because sine and cosine has the same power, so we can write this. Okay, but what we know is, we know sine A into cos A is equal to sine of 2A by 2. Is that okay? We write usually as sine 2A is equal to 2 sine A cos A. Okay, but here you can see we have sine theta into cos theta. So we can write this formula this way. And hence, if we use this formula, what we can have is twice integral 0 to pi by 2 sine of 2 theta by 2 raised to 2m minus 1 d theta. Are you getting this?
Yes,
Yes, sir.
So we have twice 0 to pi by 2 sine raised to 2m minus 1 and the angle is 2 theta upon 2 raised to 2m minus 1 and this is d theta. Okay, so that's what we got. Now, what we know, we can write this as twice here we have, this is 2 raised to 2m minus 1 integral 0 to pi by 2 sine raised to 2m minus 1 2 theta d theta. Okay, that's what we have. Now, if I want to convert this integral to beta function, then here we should not have a multiple of the angle, but we should have the angle only. So what we can do is, we can put here this 2 theta is equal to phi, and hence theta is equal to phi by 2. So we get d theta is equal to d phi by 2. Okay, that's what we have. Okay, now see the change in limit. So here theta is from 0 to pi by 2, and hence what phi will be? Phi will be 0 to pi. Is that okay? Are you getting this?
Yes, sir. Yes, sir. Yes.
Yes. Okay. So now we get, this is beta of m comma m. So we get beta of m comma m is equal to twice 2 raised to 2m minus 1 0 to pi sine raised to 2m minus 1 pi. This 2 theta we are replacing by pi. This d phi by 2. Okay, so now this 2 and this 2 will get cancelled. So we can have 1 upon 2 raised to 2m minus 1 integral 0 to pi sine raised to 2m minus 1 phi d phi. Is that okay? Are you getting this
Yes,
one?
sir. Yes, sir. Yes.
Okay. So now, if we see, this is the function sine, and in the interval 0 to pi. Okay, so here we have pi by 2, here we have pi. Okay, how you are able to see the sine curve? The sine curve is like this. Okay. So this is the sine curve we can have. It will start with 0. Okay. At pi by 2, sine will be 1. This is going to be 1. And at pi, it will be 0. So what we have to do is, we have to find the integral over this area. This is the function. We have to find the integral here on this area. So is it possible if I can make, or I can find only this area and make it twice?
Yes, sir.
Yes, sir. Possible.
Yeah, because this area is exactly twice of this area, 0 to pi, and you can see the area is positive. So we can say, if I want to find out the integral from 0 to pi, I can find from 0 to pi by 2 and make it twice. Okay, so we can have, this is equal to 1 upon 2 raised to 2m minus 1 into twice 0 to pi by 2 sine raised to 2m minus 1 phi d phi. Okay, so what I did is, I converted this integral 0 to pi as twice 0 to pi by 2. Okay. Now, what we have here, so this is equal to, what we know, integral 0 to pi by 2. Okay. Sine raised to p theta cos raised to q theta d theta is equal to half of beta p plus 1 by 2 and q plus 1 by 2. Is that okay? Is that okay?
Yes, sir.
Okay, so this is 1 upon 2 raised to 2m minus 1. This is 2 half of beta of m comma half. Okay, because if you put this as p, okay, so you'll be having p plus 1 by 2, so it will be 2m by 2, so it is going to be m. And here we don't have any cosine term, so that means q is equal to 0. So if q is equal to 0, we'll be having this half. So we got here beta of m comma m is equal to, this is beta of m comma m is equal to 1 upon 2 raised to 2m minus 1, and this is beta of m comma half. Okay, now we know the formula. So what is the formula? Beta of mn is equal to gamma m gamma n upon gamma m plus n. Is that okay? Is this formula okay? So here we have gamma m, and this is going to be gamma 2m is equal to 1 upon 2 raised to 2m minus 1. This is gamma m, gamma half, and you'll be having gamma m plus half. Are you getting this term? By using this formula, we are able to get this. So what you can cancel, one gamma m you can cancel. So it is gamma m upon gamma of 2m is equal to. So this gamma of half, what is the value of gamma of half? It is root pi upon 2 raised to 2m minus 1, and here we have 1 upon gamma of m plus half. Is that okay? Are you getting this?
Yes, sir.
Yes. Okay. So this gamma of m plus half we can take on the other hand side, and this gamma of 2m we can take on the other hand side. So what we can write is gamma m into gamma of m plus half is equal to. So it will be root pi upon 2 raised to 2m minus 1, and this is gamma of 2m. Okay. So here we got, this is called duplication formula for gamma. Okay. You can say is called duplication formula for gamma functions. Okay, so duplication formula is always for gamma function, so we don't have to worry about it. Okay, so is there any doubt in this duplication formula? We have started with the definition of beta, and then use the trigonometric definition of beta only. So after using trigonometric definition of beta, we simplified and we got the duplication formula. So is there any doubt? Now let us try to solve some examples based on the trigonometric definition of beta function, and using this duplication formula. Okay.
Sir,
Yes.
sir, actually, I have one doubt in this duplication formula.
Yes.
Sir, can you
Please.
please scroll up a little bit?
Yeah.
Yes, sir. Actually, you have written the formula, that is integration of 0 to pi by 2 sine p theta cos q theta theta. So can you, sir, please explain me from that step again?
Okay. Fine. Okay, so what do we have here? Here we have sine term, and suppose there is cosine term. So what is the power of cosine term here? 0, right?
Yes, yeah.
Okay, so what will be the term here? See, if you see, this is the power p. So p is going to be 2m minus 1, right?
Yes, sir.
Okay, so what will be p plus 1? It will be 2m. P plus 1 by 2 will be m. Is that okay?
Yes, yes. Okay.
So we got it m here. This is m here, right?
Yes, sir.
And then we have to get this q plus 1. So now q is equal to 0.
Yeah.
So if I put q is equal to 0 here, what we'll get? We'll get half
One.
only.
Yes, we get a half.
So it is a half there.
Okay, okay, sir. Fine, sir.
Got it?
Thank you.
Yes.
Yes, got it, sir.
Okay, that's good. Okay, so let us try to evaluate the integrals using the trigonometric definition of this beta function. Okay,
I want to write the formula.
yes,
Can you please scroll up a little bit?
yeah,
Thank you, sir. Thank you. Thank you, sir. I wrote it.
yes, okay, it's good. Okay, so let us think of the example. So I hope all of you are able to see this.
Yes.
Okay. So we have the example, evaluate this integral into this integral. Okay, so we got the solution. Let I is equal to integral 0 to pi by 2 d theta upon root of sine theta into integral 0 to pi by 2, and this is square root of sine theta d theta. Okay, so we can evaluate this integral as I1 into I2. So let it equation 1. Again, where we have I1 is equal to integral 0 to pi by 2 d theta upon square root of sine theta, and I2 is equal to integral 0 to pi by 2 root of sine theta d theta. Is that okay? So what I did, I just consider this as integral 1 and this as integral 2. Okay. Now we have I1 is equal to integral 0 to pi by 2 sine raised to minus of theta d theta. Is that okay? Are you getting this? Because this is square root, so it is going to be half.
Yes, sir.
It is in the denominator, so we can, if I am taking it to the numerator, it will be negative. Okay, then again the same formula, integral 0 to pi by 2 sine raised to p theta cos raised to q theta and d theta. So this is half of theta p plus 1 by 2 and q plus 1 by 2. Okay. So that's what we have. Going to be half of theta p plus 1 by 2 and q plus 1 by 2. So if we compare this integral to this integral, then what we have, this will be half of beta. P is going to be minus half. So this is minus half plus 1 by 2. And Q is going to be 0. So here we have this going to be half. Okay, so what we have here, P is going to be minus half and Q is going to be 0. Okay, now let us simplify. So we got this is half beta of this will be 1 by 4 and this is going to be half. Is that okay? Because this will be minus half plus half, it's going to be half. Minus half plus 1 is going to be half, and this by 2 is going to be 1 by 4. So we got the value of I1, or we can write I1 is equal to half of gamma 1 by 4 gamma 1 half upon gamma of 1 by 4 plus 1 half. So which is half of gamma 1 by 4 gamma half, and this is going to be gamma 3 by 4. This gamma half is going to be root pi, so it is root pi by 2 gamma 1 by 4 upon gamma 3 by 4. Is that okay? Are you getting this? So we got I1 is equal to root pi by 2 gamma 1 by 4, and this is gamma 3 by 4. Let this equation 2. So we got one of the value, okay, for this integral. Okay, and now we'll think of this next integral, right? Okay, so just think of this next integral now. What we have here, see, we have I2 is equal to integral 0 to pi by 2 square root of sine theta d theta, and this is integral 0 to pi by 2 sine raised to half theta and d theta. Again, we can use the same integral. So what we have here, integral 0 to pi by 2 sine raised to p theta cos raised to q theta d theta. This is half of beta p plus 1 by 2 and q plus 1 by 2. Okay. So now here the value of p is going to be half. So this will be half of beta half plus 1 by 2. And here again q is 0. So it will be half. So this is half of beta. Here you can have 3 by 2 by 2 and half. So this is 1 half beta t by 4, and here we have half. Are you getting this one? Is there any doubt up to it? So here we got I2 is equal to half of beta t by 4 half. So this is equation 3. So what we can write is from equation 1, 2, and 3 we get. So what is I? I is a product of 2 and 3. So it is half. Okay, what we have simplified for this? So it is root pi. Okay, so we have already simplified this. Okay, so we can simplify this more as this is equal to half of gamma 3 by 4 gamma half upon gamma 3 by 4 plus half. So it is, this will be root pi. Okay, gamma half is going to be root pi. So it is root pi by 2. This gamma 3 by 4. And here, if you see, what is going to be gamma pi by 4. So we can write this as root pi by 2. This is gamma 3 by 4. And this term, what we have 1 by 4, and this is gamma 1 by 4. Or this 2 you can cancel, and you can have 2 root pi gamma 3 by 4 upon gamma 1 by 4. Let this equation be. Is that okay? Are you getting this?
Yes, sir.
So this is root pi by 2. Okay, you can see the equation 2. This is root pi by 2. Gamma 1 by 4 into gamma upon gamma 3 by 4. So it is gamma 1 by 4 upon gamma 3 by 4. And this, so it will be 2 root pi gamma 3 by 4 upon gamma 1 by 4. So this gamma 3 by 4 will get cancelled with this. This gamma 1 by 4 will get cancelled with this. This 2 will get cancelled. So you'll be having pi into root pi, which is going to be pi. And so we can say I is equal to pi. This is what we wanted to calculate. So here, what we calculated that hence integral 0 to pi by 2 d theta upon root of sine theta into integral 0 to pi by 2 square root of sine theta d theta, and this is equal to pi. So this is what we have calculated in this example. So is there any doubt in this example?
No, sir.
So I hope all of you were able to get this. Is that okay?
Yes, sir.
Okay. Good. Now, once we are done with this, let us try to calculate, and let us try to find another example. Okay. So think of the next. So I hope all of you are able to read this. Are you able to
Yes, sir.
read this? Okay, so evaluate integral 0 to pi by 4 root of tan of 2x dx. And so we go with the solution. Let I is equal to integral 0 to pi by 4 root of tan of 2x dx. This is integral 0 to pi by 4 root of. What is tan? Tan is sine of 2x on cos of 2x. Is that okay? Because what we know is tan is sine upon cosine. So we can write this as integral 0 to pi by 4 sine raised to half 2x into cos raised to minus half 2x dx. Is that okay? Are you getting this term?
Yes, sir.
Here sine is in the numerator, square root means it is going to be half. So sine is in the numerator, so it will have the positive power. Cosine is in the negative in the denominator, so it will have the negative power. Is that okay? So this is the value of the integral I. Now, what we can do is, as we know, we don't want the multiple of angle, we want the angle here. So what we can do is put 2x is equal to theta. So we can write x is equal to theta by 2, and hence dx is equal to d theta by 2. Now think of the change in limits. Okay, so x is 0 to pi by 4, and theta will be 0 to pi by 2. Are you getting this?
Yes, sir.
Yes, sir.
So we got dx, we got 2x, and let us write this integral. And hence we get I is equal to 0 to pi by 2 sine raised to half theta cos raised to minus half theta, and this d theta by 2. So we can write half of integral 0 to pi by 2 sine raised to half. Again, we got here sine raised to half of theta cos raised to minus half theta and d theta. Now we know the formula. So what is formula? I is equal to this 1/2 remains as it is, this 1/2, and we have theta half plus 1 by 2 minus half plus 1 by 2. So in the earlier examples, q was 0, but here q is going to be minus half. And so we can have half of half into half, we can write 1 by 4. So this 1 by 4, beta of this term is going to be 3 by 4, and this term is going to be 1 by 4. So is that okay? Are you getting this?
Yes, sir.
So what we got here, I is equal to 1 by 4 beta of 3 by 4 1 by 4. So it is 1 by 4 gamma of 3 by 4 gamma of 1 by 4, and here we have gamma of 3 by 4 plus 1 by 4. So it is 1 by 4 gamma 3 by 4 gamma 1 by 4 is going to be gamma 1. So gamma 1 is going to be 1 factorial. Okay, and hence we'll be having 1 by 4. This is gamma 1 by 4 and gamma. So here we got I is 1 by 4 gamma 1 by 4 and gamma 3 by 4. So what do we know about the duplication formula? So it is m gamma m plus half is equal to root pi 2 raised to 2m minus 1, and here we have gamma of m. So what we have gamma of 2m. So here what we know is m is equal to 1 by 4. Here m is equal to 1 by 4, and then using duplication formula. What we get? So for this step, what we have m is equal to 1 by 4, and hence we can write here I is equal to 1 by 4. This m is going to be 1 by 4. So what we get here? We get root pi upon 2 raised to 2 into 1 by 4 minus 1, and this is gamma 2 into 1 by 4. So we can simplify this as 1 by 4 root pi, and this term what will be having 2 raised to. Okay, this is going to be half. So here we get minus half. This is gamma of half. So what we know? 1 upon 4. This is root pi. This gamma half is again root pi. and this 2 raised to minus half. So 2 raised to minus half. That's what we have. 2 raised to minus half. So 1 by 4, this is 5. And I can write this as 2 raised to half. Is that okay? Are you getting this? So we got I is equal to. So here, this is going to be root 2 pi upon 4. So can we write it as pi upon root 2? Can we write it like this? Because 1 to root 2 we can cancel, no?
Yes, sir.
So we got here I is equal to pi upon 2 root 2. And hence, this is what we have. We got the value of this integral to be pi upon 2 root 2. Is there any doubt in this example?
No, sir.
All of you got this example?
Yes, sir.
Yes, sir.
Okay, that's good. Okay, so this way we are able to get the value of the integral in terms of beta, and once we get the value in terms of beta, we are able to get the value in terms of gamma. Now, we have seen the beta and the gamma function. Okay, so we know how to simplify the beta function, how to simplify the gamma function, how to relate beta and gamma function. Now, we need to understand how to differentiate under the integral sign. Okay, so now we'll try to understand the differentiation under integral sign. Okay, so let us think of the differentiating the integration. Okay. Differentiation under integral sign, or in short, we call this as DUIS. Okay, so what is the meaning of differentiation under integral sign? So suppose we have a function, let f of x lambda be the function of x and lambda such that double f by double lambda is continuous in x and lambda. Okay, and this is the function f of x lambda. This function is the derivative of this function is going to be continuous. Okay, so when I say this function is differentiable, that means the function itself is a continuous. Okay, so its derivative is continuous in x and lambda. Okay, now if we have integral from a to b f of x lambda dx. Okay, so try to understand this integral. A and b are the limits of x. Okay, a and b are the limits of x, So when we integrate this with respect to x and we put the values of x as a and b, then this function will be in terms of lambda only. This function will be in terms of lambda only, and that's why we call this as the integral of lambda. Okay, so if we have this integral and this condition is satisfied, then we can differentiate this integral. Okay, because I of lambda is the function of only one variable, lambda. Okay, so we also call this lambda as a parameter. Then we have to differentiate. When we have one variable, we have to differentiate totally. So that's why d. But if you see inside the integral sign, then this is a function of two variables, x and lambda. And that's why we have to go with the partial derivative. So we have dabba by dabba lambda of f of x lambda, and then okay. So that's what we have. This is the differentiation under integral sign with one parameter. Okay, so here lambda is also called as parameter. Okay, so we can write here where lambda is parameter. Now, how to relate this DUIS and the earlier topic? So we can see that in gamma, apart from the variable, there is one parameter n. In beta, apart from the variable of integration, there are two parameters m and n. Okay, so all the results, whatever we have obtained for gamma, can be obtained using DUIS with n as a parameter. And all the results of beta can be obtained using DUIS with m and n as parameters. Okay, so that's what we have this differentiation under integral sign when the limits of the integration are going to be constant. Okay, so is there any doubt in this definition? Is there any doubt in the definition?
No, sir.
Okay.
No, sir.
Okay, that's good. So we'll see some examples based on differentiation under integral sign. Okay, so I hope you got the idea for this DUIS. We'll go with the example. Evaluate integral 0 to infinity e raised to alpha x sin x upon x dx, and hence find the value of integral 0 to infinity sin x upon x dx. So this is what we have to find. Okay, so think of this integral that I is equal to integral 0 to infinity e raised to alpha x into sin x upon x dx. So here we need to understand what is the variable and what is the parameter. So how we are able to find the variable of the integration. Okay, so what we have here, we have dx. Okay, so this is what we have, dx. So this is going to be the variable of the integration. Okay, and apart from this variable, whatever the term we have, that is going to be parameter. So what we have apart from x? Alpha. So alpha is going to be the parameter, and hence this integral will become integral of alpha. Okay, so we identified the variable and we identified the parameter. So let this equation 1. Okay, so we consider this as equation 1. Now we write here using differentiation under integral sign with alpha as parameter. Okay, so we always have to declare what is going to be the parameter. So here alpha is going to be the parameter, then we get, okay, so what we are able to get, di by d alpha is equal to integral 0 to infinity dabba by dabba alpha, and here we have e raised to minus alpha x sin x upon x dx. Is that okay? We're getting this step. Now here inside the integral we go with the partial derivative, outside the integral we go with the total derivative. Now in partial derivative, when we differentiate with respect to one variable, the other variable is treated as a constant. So here we are differentiating with respect to the parameter, and hence this term sin x upon x, these terms are not containing alpha, so these terms can be treated as a constants with respect to alpha. So dabba by dabba alpha and e raised to minus alpha x dx. So what we know d by dx of e raised to ax is a times e raised to ax. But here we are differentiating with respect to alpha, not with respect to x. So x will be treated as a constant. So here x will be treated as a constant. So we'll be having integral 0 to infinity sin x upon x, and the derivative is minus x e raised to minus alpha x dx. Are you getting this derivative?
Yes, sir.
Okay, because we are finding the derivative with respect to alpha, not with respect to x. So this is important step. So we are differentiating this term partially with respect to alpha, and hence x is going to be constant. So this x and this x will get cancelled. We can have minus integral 0 to infinity e raised to minus alpha x sin x dx. So we got here di by d alpha is equal to minus integration 0 to infinity e raised to minus alpha x sin x dx. Is that okay? Are you getting this?
Yes, sir.
Okay.
Yes, sir.
So now we have to integrate this. So what is the formula? We have integral e raised to ax into sine of dx plus c dx is equal to e raised to ax upon a square plus b square, and here we have a sine of dx plus c minus b cos of dx plus c. So this is the formula for the integration. Now let us integrate this. So di by d alpha is equal to, this minus sign remains as it is. Now e raised to minus alpha x. So this becomes alpha square plus 1, because here the value of a is going to be minus alpha. So minus alpha square is alpha square, and the value of b is going to be 1, c is going to be 0. So alpha square plus 1. Now here minus alpha sin x and minus cos x, and the limit is 0 to infinity. Okay. So now see, this is going to be minus. if we put x is equal to infinity, then this e raised to minus x is going to be 0, because we have e raised to minus infinity. So e raised to minus infinity is going to be 0. So this term is going to be 0. Minus the lower limit. So e raised to 0 is going to be 1. And here we have alpha square plus 1. Sin 0, 0. Minus cos 0 is going to be 1. So we have this minus, and this minus. So it will become minus 1 upon alpha square plus 1. So what we get here, we get di by d alpha is equal to minus 1 upon alpha square plus 1. This is a variable separable differential equation. So if it is a variable separable differential equation, what I can write is di is equal to minus 1 upon alpha square plus 1 d alpha. Are you getting this step?
Yes, sir.
Okay. So what we can do is integrating. We get. Okay. So let us integrate. If we integrate this, what will be having? This is integral di of alpha is equal to integral minus 1 upon alpha square plus 1 d alpha. And when we don't have the limits, we have the constant of integration. So this is the integration of di is I, and the integration of this is going to be cot inverse of alpha plus c. You're getting this?
Yes, sir.
Are you getting this integral?
Yes, sir.
Okay.
Yes, sir.
So let this equation 2. Okay. So now see the given integral we have considered as equation 1. This is the given integral. We have considered it as equation 1. And now we got I is equal to I of alpha is equal to cot inverse of alpha plus c. We have to decide the value of c. Okay, so if I want to decide the value of c, what we have to do is we have to initialize the given integral. So think of the value of alpha such that this integral becomes 0. So what is the value of alpha you can think so that this integral 1 will become 0.
So infinity.
Yes, it is easy, infinity. So if we put alpha is equal to infinity, then I of infinity is going to be 0. So what we do here, put alpha is equal to infinity, we get. So we have I of infinity is equal to cot inverse of infinity and plus c. So I of infinity is 0, cot inverse of infinity is 0, and hence what we get, c is equal to 0. Is that okay? Are you getting the value of c? Are you getting the value of
Yes,
c?
sir.
Yes.
Yes, sir.
So what we can say is from equation 2 we have, so what we get, I of alpha is equal to cot inverse of alpha. Or what is I of alpha? I of alpha is integral 0 to infinity e raised to minus alpha x sin x upon x dx, and that we have obtained as cot inverse of alpha. So let this equation 3. Okay, so we wanted to evaluate this integral. Okay, so we got the value of this integral. Now see what we want the next. We want to solve this integral also. So how to obtain this integral from this integral? So can you see any relation between this integral and this integral?
alpha is equal to 0, we get the
Yes, it is easy to guess that if we put alpha is equal to 0, then we are able to get this integral. So we have obtained the equation 3, okay, where we know this integral. And hence, what we can do is, we can put alpha is equal to 0 in above equation. So we get, what we are able to get is integral 0 to infinity sin x upon x dx, and that is going to be cot inverse of 0. So what is the value of cot inverse of 0?
pi by 2.
Yes,
Pi
it
by
is going to be pi by 2. So here we got the value of this integral 0 to infinity sin x upon x dx, and that is going to be pi by 2. So we have, it is going to be pi by 2. So this way we are able to use the differentiation under integral sign to calculate the values of the integrals. Okay, so here we calculated the value of the integral using the differentiation under integral sign. Yeah. Yes. So how we get integral this I of infinity equal to 0, right? So we have this integral, equation 1. Okay. Now, if I put here infinity, what will be the value of e raised to minus infinity?
0.
Zero.
Yeah. So e raised to minus infinity is going to be 0. So e raised to minus infinity is 0. So what will happen to this integral? This integral will be 0. That's why we have written I of infinity is equal to 0. Is there any other doubt?
No, sir.
Okay. So all of you got this example. Have you got this example?
Yes, sir.
Yes, sir.
Okay, that's good. Okay. So now we can think of the another example. Okay. So let's have the another example. So I hope all of you are able to see this. Are you able to see this example?
Yes, sir. Yes, sir.
Okay. So here the question is prove that the integral 0 to infinity log of 1 plus ax square upon x square dx is equal to pi root a when a is going to be greater than 0. Okay, so let us try to solve this example. Okay, so what will be having I is equal to integral 0 to infinity log of 1 plus ax square upon x square dx. What is the variable of integration?
X,
sir.
What is the parameter?
A.
A,
What is the parameter?
A, sir. A for apple.
A.
A, correct. So A is going to be the parameter, X is going to be variable. So from here, you can check that what is going to be the variable. So here, if A is a parameter, that means this is integral of A. Okay, A is a parameter means what? It is integral of A. So we can say here, using differentiation under integral sign with a as parameter. We get, okay, so what we are able to get, di by dA is equal to integral 0 to infinity dabba by dabba a, and we have log of 1 plus ax square upon x square, and this is dx. So this is equal to integral 0 to infinity. 1 upon x square is going to be constant. So dabba by dabba a, and we have the term log of 1 plus ax square dx. So this is equal to integral 0 to infinity 1 upon x square. The derivative of log is going to be 1 upon 1 plus ax square. But again, the derivative of this function is going to be x square, because we are differentiating with respect to x, not x. So we have to be careful that we are differentiating this function with respect to a. So the derivative of 1 will be 0, the derivative of a is going to be 1, and hence here you have x square dx. Now this x square and this x square will get cancelled. Okay, so what we get here, we get di by dA is equal to integral 0 to infinity 1 upon 1 plus ax square dx. So if we take this a out, we can have 1 by a integral 0 to infinity dx upon 1 by a plus x square. Are you getting this term? I have taken this a out. Okay. And then we have the formula integration dx upon a square plus x square is equal to 1 by a, and this is tan inverse of x by a. Okay, so if we use this formula, we'll get here, we get this 1 by a remains as it is, and now the integral 1 upon 1 by a, but this is a square. If we compare, this should be actually a square, and hence here we have to think this will be root of a into tan inverse of x upon 1 by root of a, and here the limit is 0 to infinity. So we got here, this is 1 by a, this will be root of a, tan inverse of root a into x, and then we have the limits 0 to infinity. So this is equal to 1 upon root of a, and we have tan inverse of root of a into x 0 to infinity. So this is equal to what we get here, 1 upon root of a, and here we have tan inverse of infinity minus tan inverse of 0. So 1 upon root of a. What is the value of tan inverse of infinity?
Pi by 2.
So this is going to be pi by 2, and this is 0. So we get pi upon 2. So we got di by dA is equal to pi upon 2. Okay. Now this is again a variable separable differential equation. So di is equal to pi upon 2 root a dA, and hence we can integrate this. So integrating above equation, we get. Okay, so what we are able to get, integration dia is equal to integration. This pi by 2 is going to be constant. So 1 upon root a EA plus C. Here C is going to be the constant of integration. So this is integration of EA, and this is pi by 2. This is 2 root A plus C. Or we can write I of A, this is equal to pi root A plus C. This is going to be equation 2. Now we have to find the value of C. Okay, so when we want to find the value of C, what we have to do is we have to initialize the integral. So think of this integral 1. Okay, so let this equation 1. Now think how we are able to make it 0.
A is equal to 0.
A is equals to.
Are you getting this? If we put A is equal to 0, then this will be 0.
Yes, sir.
So if we put this A is equal to 0, then what will happen? This will be log of 1. Log of 1 is going to be 0. If log of 1 is going to be 0, then this entire integral becomes 0. That's why what we have to do is we have to put A is equal to 0. So if I put A is equal to 0, so put A is equal to 0 in above equation 2, we get. So what we have here? We have I of 0 is equal to, this A is going to be 0. So this term is going to be 0 and plus C. I of 0 is 0 plus C. So what we get? C is equal to 0. We get here C is equal to 0. So what we can say from equation 2, we have what we can write is I of A is equal to pi. That is what we wanted to prove. Integral 0 to infinity log of 1 plus ax square on x square dx is equal to y. So this is what we wanted to prove. Okay, or we wanted to here what we wanted to. This is what exactly we wanted. Why? Is there any doubt in this example? Is there any doubt in this example?
No, sir.
Okay, so all of you got this one.
Yes, sir.
Okay. So easily we are able to get the value of the integral, and this is how exactly we need to use differentiation under integral sign. Okay. Now, what exactly we do when we apply differentiation under integral sign? Okay, so here we consider 3 steps. First, we use differentiation under integral sign, simplify the integral and integrate it. After integrating, we always get the variable separable differential equation, and once we get the variable separable differential equation, then again we integrate with respect to the parameter so that we get the answer. Okay, So when we try to evaluate the integral, if we are not able to integrate it directly, then we try to remove the term which we are not able to integrate easily. Okay, and then we integrate. Or sometimes our parameter will get free or removed from the given term, and then we are able to integrate. There is no restriction on how many times you can use differentiation under integral sign. So if required, you can use it twice, thrice, like that. Okay. So here, basically, when we are not able to integrate, or we have more than one term or two terms, because if we have two terms, we are able to apply the rule u into v. Okay. But if we have more than two terms, then we are not able to apply the rule integration of u into v or by parts formula. And that time, this differentiation under integral sign help us. Okay. So let us try one more example using differentiation under integral sign. So if you have any doubt, you can ask, or we'll go for the next example. So if there is doubt, please ask, or we'll go for the next example. Is there any doubt?
No, sir.
So let us think of the next example. Okay, so we have another example. Evaluate this integral. So we have let I is equal to integral 0 to infinity e raised to minus x by x a minus 1 by x plus 1 by x e raised to minus ax dx. So this is integral of a. Is that okay? X is a variable of integration, and then the a is a parameter. Now what we can do is, using DUIS with a as parameter, we get. So what we have, di by dA is equal to integral 0 to infinity dabba by dabba a, and we have here e raised to minus x by x a minus 1 by x plus 1 by x times e raised to minus ax and dx. Are you getting this term? So we can have integral 0 to infinity. This term is free from a, so it remains as it is, or treated as a constant as we are taking the partial derivative. Now what we have, dabba by dabba a of a minus 1 by x plus 1 by x into e raised to minus ax dx. So this is equal to integral 0 to infinity e raised to minus x by x. The derivative of a is going to be 1. The derivative of this term is going to be 0. The derivative of this term is plus 1 by x into minus x e raised to minus ax dx. Are you getting this derivative?
Yes,
Here
sir.
we are differentiating with respect to a. So x is treated as a constant. And hence we have integral 0 to infinity e raised to minus x by x. And here we have 1 minus e raised to minus ax dx. Are you getting this term? So here, this x and this x will get cancelled. Now we got di by dA is equal to integral 0 to infinity e raised to minus x, 1 minus e raised to minus x upon x dx. So still we are not able to integrate this integral. Okay. So what we can do is, again we can use DUIS. So again, using DUIS with a as parameter. So we have already decided a as a parameter. So we get. Now what we'll have here, I'll have the second order derivative di by dA square. And this is integral 0 to infinity dabba by dabba a e raised to minus x 1 minus e raised to minus x upon x dx. So is that okay? Are you getting this? So what we get here, integral 0 to infinity e raised to minus x upon x. This is dabba by dabba a 1 minus e raised to minus ax dx. So it is integral 0 to infinity e raised to minus x upon x, and here the derivative of this term is going to be 0. So here we have minus, and this minus x will become plus x. So e raised to minus ax dx. Are you getting this derivative?
Yes,
You're getting this derivative. So here we are finding the derivative with respect to a. So minus x will be treated as a constant. Here we have minus already, so that becomes plus x. Okay, this x and this x will get cancelled. So I got here d2i by dA square is equal to integral 0 to infinity e raised to minus x e raised to minus ax dx. Or we can say this is integral 0 to infinity e raised to 1 plus a minus x dx. Okay, and that's what we have. Now think of integration. So d2i by dA square is equal to integral 0 to infinity e raised to minus a plus 1 x dx. So the integration is going to be minus e raised to minus a plus 1 x upon a plus 1, and this is 0 to infinity. Are you getting this one? Are you getting this integration? Yes. Okay. So I can take this minus 1 upon a plus 1 outside, and I have e raised to minus a plus 1x, and the limit is 0 to infinity. So minus 1 upon a plus 1, and here we have. If I put e raised to minus infinity, then this term is going to be 0. Minus, we have e raised to 0. Because x is going to be 0. So we can have minus 1 upon a plus 1. And here we got, this is minus 1. So we can have 1 upon a plus 1. So we got here d2i by dA square is equal to 1 upon a plus 1. And this is going to be the variable separable form of a differential equation. So I'll be having this term. Now integrating above equation we get. So what I have here, this I can write as d by dA of di by dA, and this is 1 upon the integration, a plus 1. So what will be the integration of this term? So we'll be having integration of d2i by dA square. This is equal to integration 1 upon a plus 1 with respect to dA. Okay. So plus c. This integration will be di by dA because we have a second order derivative. If we integrate, we'll have first order derivative, and that is equal to, what is the term you will be having here? So this is log of a plus 1 plus c. Now here we have this is the integral, this equation 2. We can write. Okay. The given is equation 1. This di by dA is equation 2. Now we get this is equation 3. Okay. So I am integrating once. So I'll consider this as C1. Now we want to find the value of C1. So that means we have to think of this term di by dA. And the term di by dA is in equation 2. So what we can put the value of a so that the integral in equation 2 becomes 0. Okay, this is the integral that we want to make 0. So what is the value of a? We should put?
0.
We have to put a is equal to
0.
0.
Okay. So let us put a is equal to 0. So what we can do is put a is equal to 0 in above equation. We get. So what I get is di by dA at a is equal to 0, and this is log of 0 plus 1 plus C1. So we know this is going to be 0, this term is going to be 0, and this is going to be C1 plus C1. So what we can say is C1 is equal to 0. So we get C1 is equal to 0. And once we get C1 is equal to 0, we can put this in equation 3. Okay, so what we can write is from equation 3, we get, so we have di by dA is equal to log of a plus 1. So now, again, this is variable separable. So di, and this is log of a plus 1 dA. What we can do is integrating above equation, we get. So what we are able to get here, see, integration dia is equal to integration log of a plus 1 dA plus c. So here we want to find the integration of log. So this is going to be integration of a. What will be the integration of log? What we know, what is the integration of log?
X log x minus x.
So it is going to be x log x. Okay, but here we have log of a plus 1 also. Okay, so here we have a plus 1. So what you can do is integration log of a plus 1 into 1 dA plus c2. What we know, integration of u into v, u as it is integration of v minus derivative of u integration of v. This is what the formula is. Is that correct? So here this term is going to be u and this term is going to be v. So log of a plus 1 integration of dA minus integration, the derivative of log is going to be 1 upon a plus 1, and the integration is going to be dA, and then this will be dA plus c. Okay, now simplify this. Okay, so we get here the integration of A is equal to the integration of D is going to be A log of A plus 1 minus integration 1 upon A plus 1. And here this is going to be A plus C. So it is A log of A plus 1 minus what you can have here A upon A plus 1 dA plus C2. So this is A log of A plus 1 minus. Can we write this as A upon A plus 1 is equal to A plus 1 minus 1 upon A plus 1. So it is 1 minus 1 upon A plus 1. Can we write this term like this?
Yes, sir.
So when we have this is 1 minus 1 upon A plus 1 dA plus C. So this is equal to, okay, what we can have A log of A plus 1 minus the integration of this term is going to be A plus the integration of this term is going to be log of A plus 1 and plus this is going to be C. So we can have this is A plus 1 log of A plus 1 minus A plus C2 and this is I of E. Okay, so this is equation 4. Now we want to find the value of C2. Okay, so if we want to find the value of C2, we have to go to equation 1. Okay, so think of the integral I. So what value of A will make this integral 0? So think over this now. What value of A will make this integral 0?
0, sir.
Yes.
0.
Again, it is going to be A is equal to 0. So if I put A is equal to 0, then this I of A is going to be 0 or I of 0 is going to be 0. So what we can do is put A is equal to 0. We get, okay. So I of 0 is equal to 0 plus 1 log of 0 plus 1 minus 0 plus C. So this is 0, this is 0 minus 0 plus C2. And hence we get C2 is equal to 0. So we got the value of the constant of integration and that is going to be 0. And hence from equation 4 we write from equation 4 we I of A is equal to A plus 1 log of A plus 1 minus A. Here we got the value of the, okay, or we can say that is the integration we know. Okay, so integration 0 to infinity e raised to minus x upon x a minus 1 by x plus by x e raised to minus ax x. This is equal to a plus 1 log of a plus 1 minus. So this way, using the differentiation under integral sign, we are able to evaluate the integrals. So is there any doubt in this example?
So can you please scroll a little bit up?
Yes.
Okay, sir.
Okay. Done.
Yes, sir. Done.
So that's good. Okay. So if you have any doubt, you can ask. Do you have any doubt? You ask now. Is there any doubt?
No, sir.
Sage, any doubt?
No, sir.
No.
Prajakta, any doubt?
No, sir.
Okay, that's good.